This is a tutorial designed for helping those involved with the Zooniverse project Planet Hunters TESS. It is a citizen science project, so anyone can contribute as long as you have a computer and internet. TESS is a exoplanet hunting satellite launched by NASA in April, 18th of April 2018 as a successor to the Kepler Space Telescope. The main objective is to detect planets using the transit method. The About page gives much detailed information about this project, which I suggest you read before beginning. But to begin, once you've done that, press the Classified tab. So here you have the main screen upon which you'll be working on. This is known as a light curve, with brightness on the y-axis in percentage and time on the x-axis in days. Every one of these little dots is a measurement of the target star's brightness, and it goes for a period of around 27 days for every sector of the sky that TESS is scanning. So there's one dot for every 30 minutes, so ultimately there'll be 48 measurements a day if everything's working perfectly. What we are looking for are events that are known as transits, which is when a dimmer, much smaller object passes in front of the target star that is being measured, and it will block a portion of the incoming light, and so it will therefore reduce the brightness measured, and it will look like a dip on the light curve. There's an animation down here which will show you. See the planet coming towards it, and brightness dips, and when it's gone past out of sight, the measurements will go back up to normal. So on the light curves we'll be looking at, transits will look like this and this. Most transits on these light curves will occur more than once, so you'll be able to get a rough estimation of the orbital period of the object that is transiting. In this case, it looks like it's roughly 18 days between transit events. The depth of this dip of this transit event is a main indicator for the potential size of the object. In this case, it blocks roughly 0.25% of the star's light. Some curves have gaps of data where there's no measurements were taken because of either maintenance or other varying reasons, and this curve happens to be one of them. There could be another transit in this data gap, but this is not known for sure. So to mark a transit event, you need to make sure the annotate button is selected and drag using left click to highlight the area upon which you can see a transit. So I'll put one there, and I'll put one there. You can also zoom in to have a more accurate view of the light curve and any possible transits. So let's have a look at see. Yeah, you can see it's definitely a transit event. You can zoom back out for using this button. You can reset the subject view. So if I just zoom in, then press that, it will go back to default. If you've made a mistake, like if you did that, then you can change the length of the transit, or if you want to just delete it, you press this X button up here, as so. To find out more information about the target star that you're looking at, you need to press the subject info button. So it'll give us a few basic details about the star. So what TESS sector it's in. So in this case, it's in sector 24. The magnitude of the star, which is how bright the star is when observed from Earth. Surface temperature in kelvins. So it's 6081. And the solar radii, which is 1.253. So this star is slightly hotter and slightly larger than our own sun. There's a way to get more information about the star, but I'll show you later. But the info we got here indicates that a transiting object that we've found is likely to be a planet rather than a big eclipsing binary star. But to know for certain, we need to work out the radius of the planet. To find out the radius of the planet, we need to follow this equation. So we got the solar radii, the radius of the star times the square root of the transit depth. So in our case, it will be 1.253 times the square root of 0.25. And if I get this here, so the result we'll have will be 0.6265. The end result will be in Jupiter radii. So this is how big one will be the size of Jupiter. So to put things into perspective, these are all of the major bodies in our solar system, with the numbers above them is their value of their radius in Jupiter radii. So Jupiter is 1, Saturn 0.833, and so on and so on. The Sun is around 10 Jupiter radii. A body that's anything over than roughly 1.5 Jupiter radii is unlikely to be a planet. So, but the object we have found is in between the size of Saturn and Uranus. So it's closer to Saturn in size. So it's going to be classified as a sub-Saturn planet. And we don't talk about this just ever. Eventually, if you do this calculation often enough, you'll be able to tell the difference between a planet or an eclipsing binary just from looking at the solar radii and the transit depth that you've been given. And just from doing that, we have found the radius of the planet and its orbital period. So it's good. There is a field guide here which can give you more information about the features that you're looking at. So if we look here at eclipsing binaries, you can see the features that what eclipsing binary will look like, because you see there are various different types of them. Some are insane, some are really fast orbiting, some are really, really strange. Yeah, lots of information about what transits to look for, how to identify them, information about glitches and systematic effects, and how to tell the difference between stellar variability and a transit. There is also an inbuilt tutorial, but it pretty much just repeats what I've just said, just how to mark a transit and how to do it. If you have a Zooniverse account, which I recommend you do get one or sign up for one when you're trying to do this, and you can catalog your favorite subjects. So if you've found a planet like this one, you can add it to favorites. If you can make collections, so you can organize the stars that you found. As you can see, I got a wide range of different types of stars and transit events. And once you've done all this, you can press done or done and talk. Done makes you means all the transits you've done will be saved and into the Planet Hunters database, and then you'll get a new light curve to classify. Or if you found something interesting, like I have here, then I'm going to press done and talk, because then you can share it with others, and others will be aware of what you found. So once you've classified a a curve, and this screen pops up, it means that's the curve you classified is a simulated one. So the transits there are not real or raw data. Um, you shouldn't feel discouraged if you think you found a planet and it turns out that it doesn't exist at all. Um, uh, the more classifications you do, the less often you will encounter this, and it doing it helps the researchers out significantly with constructing their models and their algorithms. There's more information about it in the about page at the top, and then go all the way down to simulated data. There's a few paragraphs that explains why it's um, in the project. So this is the talk page. This is where it starts to get a bit more complex. So you don't have to do this stage if you don't particularly want to, but if you're interested in what you're looking at, then I recommend you do this. And once you're on this screen, you can't go back and um, reclassify the subject you just at, and you can't use the same tools as before. So you need to make sure that you have got all the information, all the important information that you need. Here is another interesting object that I've just found, which is this one is not simulated, so this is real uh, measurements and real data. The star is just over half of the size of our own sun, and the possible radius of this object is potentially that of another sub-Saturn planet. Its orbit is extremely quick around its star, roughly twice a day, so it's extremely close to its parent star. It's very, very hot. Here you have the option to put notes about the subject that you are describing. Here you have an option to invert the color if you think this is a better way to view the measurements. And here is more information about the star. So here we have a TIC ID, which is the designation this star has been given for the TESS project. And here we have a link to ExoFOP, otherwise known as the Exoplanet Follow-up Observing Program. So let's click on it. So this is where professional astronomers place their notes in public for anyone to view about the certain star that they're looking up. For this object, there's not a massive amount of information about it. It's not a object of interest. There's no known planet, from what we know. There's a stellar that has no known companions, and there's no real observations about it anywhere. But there is more measurements about the star, and there's more accurate details. You have information about the mass of the star, the density, luminosity, and how far it is away from us. I will show you later another object, which there are plenty of observations on here with various different astronomers inputting their, their observations. But what we need to do now is, if you've acquired all the relevant information, you need to check if there's what is known as a threshold crossing event, or TCE for short. This means we have to go to another site, which is ExoMAST. This will tell us if the object we have is already been flagged as a possible candidate. So we need to copy the TIC ID from here and implant it here. Oh, and adjust. Yeah, here we are. We have a report here. So let's click on it. Even though it's in Sector 18, it's still relevant to us. So here we have much more accurate data about the possible planet that we found, rather than the estimations we made. So we have its exact radius, its period, up to many decimal places, its approximate temperature. We've got similar details about the star itself as well. Down here is all the different telescopes and instruments that have observed the star. And here is how long, well, roughly how long the star has been observed for. Here is it's the same curve that we originally looked at, but in this case it's been folded along where the transits are at a single point. So it's got so this gives us a nice smooth curve. The even and odd things are the checked similarity between each other to rule out a possible eclipsing binary. Because if these were different, then it would indicate that it is a binary. But what we primarily came here for is the vetting summary, which is what I'm going to download here and open. What we have here are multiple different views of the curve, and I'm not going to pretend that I understand it all because I don't. But the top one here is basically just the standard view of the whole curve with all the transits view. This one is folded, but is sorted into days, and this one's the same, but is sorted into hours. This one is the even odd binary check. You see it's okay for this. Not entirely sure what this means. This checks the amount of transits, the signal to noise ratio, or the SNR, and that's is pretty good. But what's most important is the results down here. We have a pair of red flags here, which are both to do with the centroid offset. And as you can see, the target star of where the centroid should be is in red. The blue ones are different TIC objects, and it's pointing towards different area of the sky. As you can see here, it's 9 and 10 seconds away, depending on which variant of centroid you look at. This basically means that the measurements of the star on the star by TESS have been affected by contamination of some form, usually because of these stars or by a nearby eclipsing binary, which means this object is unlikely to exist. The results from this are deviated from this full vetting report, which is a full report of all the different results that you can see here and all the data that is accompanied by it. And all these are necessary to see if there is a possible planetary candidate or not. And if one of these is a red flag, then it's likely that there isn't a planet there at all. And you can see there's a wide range of data, which if you're interested, you can look at and observe in your own time. One way to check contamination, if before we have to look into all this, is if we go back to ExoFOP, we have a contamination ratio up here. As you can see, it's 0.23. Now, a good candidate usually has a ratio of less than 0.1. Um, Anything above 0.2 is unlikely to be a candidate. But I've never seen a candidate which is higher than 0.35. So it's ideal if you want to. You should always be cautious if you find a possible planet. You should always check this, and also, of course, the vetting summary. Um, Another way is to see how many nearby stars are nearby and see how crowded the area is. If it's a highly crowded area with hundreds of stars in the same area, then it's likely was more likely to be contaminated. So now we've found out as much as we need to know about this possible candidate. So we're ready to put some notes on it. So first is just some physical descriptions. So um, transits roughly as per day. Then I think it's ideal to mention the TCE. So copy the link of this here, so others can check the same TCE, and then just tell them about the results of the vetting summary. So centroid offset in your vetting summary indicates that this affected by and unlikely to exist. I think that's everything that you need really for this candidate. Yeah. So add the comment. And there we go. The comment is now there for everyone to see. So now I should show you a good candidate instead of this one. Here is a possible candidate that is in the same sector as the previous one. As you can see, there's clear and obvious transits every, well, roughly 4.5 days. I did the radius calculation, and that indicates that the object is roughly similar to that of Saturn. And as you can see, I've already placed a comment here, and I already added it to my list of planetary candidates, as well as someone else. For this object on ExoFOP, you can clearly see that there's much more information than there was the last one, because this TOI, this is a TESS object of interest, or TOI for short, and this is TOI 1408. You can see more details about the planet's possible parameters. You can see it's roughly 8 times the size of Earth. The transit duration, how deep the transit is, period, how long it orbits. So it orbits once every 4.5 days, which means it's very hot. So it's likely to be a very hot planet. There's updated stellar parameters. You can see down here there's much more observations done from different telescopes. These are This is not from TESS. This is from different telescopes to TESS. Follow-up observations. You can see spectroscopic. Do that's to do with the incoming light wave frequencies. And there's a time series observation as well, which I don't see many of these often. 372. There's a whole bunch of files you can download and see, and to see what these people are doing. There's a couple more notes here. These are using the TESS telescope to they're observing velocity movements of the planet, or the possible planets, and so far it looks good from reading that. You see the contamination ratio is very low, and the star is only 9 targets in 1 arc minute, so it's relatively low zoned. Another thing is that you can use this. This is SIMBAD, which is part of the University of Strasbourg, where they have a massive catalogue of stars. And you can see a few more details about the spectral type of the star. So this is an F8, so it's larger than our sun, larger and hotter. And you can see on this is a photo of this target star here. You can see it's clearly on its own and not a massive crowd. This star, of course, has a TCE, so I've already put it in, and you see the planetary system and the radius of the planet is, well, larger than my rough calculation. So it's slightly smaller than Jupiter, but still big enough to be classified as a hot Jupiter. And this is the vetting summary for it. You can see the transits are clear and pointed out with the blue triangles. This is the folded curve. This is the folded curve in ours. And yeah, you can see all the rest. The centroid, there's no other measured star near it, and it's very close and within acceptable limits. So because it's a TOI, then it's very likely this object's going to continue to be researched within the foreseeable future by professional astronomers. I know I've not shown you everything yet, but especially what to do when classifying eclipsing binaries, strange stellar variability, and other strange phenomena. So I'm going to make a second video after this, which will go through classifying several light curves so you can get a better understanding of what to look for when trying to find some transits. If you have any questions or wish to correct any errors, then don't hesitate to comment. Thank you for your time.